In this video, we're going to talk about the famous experiment of Thomas Young, namely the double slit experiment, which demonstrates for us that light is indeed a wave. Now, it's also a particle, but in this video, we're going to be talking about that light is indeed a wave, because when we add light together, we either get bright spots or dark spots when it comes from two sources. We either get a light fringe or a dark fringe. So light experiences constructive and destructive interference, which only waves do, and that's what we're going to be talking about today in terms of calculations. So stay tuned till the end, and we'll talk about why this is so important in terms of waves and things that you'll see out there in the real world, and why the wavelength and the sources of waves are so important as it relates to this object process diffraction. So let's get into today's video. Coherent light of a single frequency passes through a double slit with a separation d to produce a pattern on a screen a distance D from the slits. What would cause the separation between adjacent minima on the screen to increase? If we want spacing between the fringes to increase, what we want is we want more diffraction. In other words, we want more spreading out of the light. And that happens when it's longer wavelength. So if the wavelength goes up, remember sound has a much larger wavelength than visible light. So if the wavelength goes up, that means there's more diffraction and the fringes should spread apart. That would be when the frequency goes down, because if the wavelength is going up, the frequency should go down. Now that would be not choice D. Other choices are increase the distance D. So if you increase the distance D, the angle stays the same, but I think the distance between the points would also increase. Increase the index of refraction of the medium. So if you increase the index of refraction of the medium where the setup is immersed, the light has the same amount of diffraction, but just moves slower. So it's not going to be B. C, increase the separation between the slits. Now that's going to actually cause the fringes to move together. And the reason is because if the slits are further apart, there's more possibilities for interaction in between, and so the fringes move together. So it's not going to be C. So yes, it will be A. And the reason you could think about it is because if you've got these fringes, but then you move the screen back, so imagine this screen has been moved back. Okay, so imagine this is kind of three-dimensional. This fringe is going to be over here, and this fringe is going to be over here, and that's because, imagine that right triangle I showed you on my computer screen the other day. The angle to the fringe stays the same, but if you move the screen back, the fringes have just moved apart. Does that make sense? Let's have a look at number 4. Substituting tan theta for sine theta results in what percent error for an angle of 5 degrees? Probably tan of 5 degrees minus the sine of 5 degrees divided by the sine of 5 degrees. Think of tan theta as our experimental value, and sine 5 degrees is sort of our original value. Let's see, I gotta make sure this calculator's in degree mode. Tan 5 minus sine 5 over sine 5. And remember, the small angle approximation says we shouldn't have much error. So I've got 0.00381, and we want that as a percentage. So that would be this. Nicely done. In the Young's double slit experiment, a fifth order maximum occurs at an angle of 1.422 degrees. If the screen is 3.90 meters from the slits and the slit separation is 0.135 millimeters, what is the wavelength being used? So diffraction interference maximum is d sine theta bright equals m lambda. Remember, m is an integer there. It's the fifth order maximum. I think m is 5. We're looking for lambda. D is the separation between the slits. Now remember, sine of theta, we're going to approximate that as tan theta, just like we've discussed, especially since this angle is so small. The tan of theta is approximately, let's see, so you got to think about the right triangle. It's basically going to be y over L. And y is like how far from the middle of the central bright fringe you go up. L is the distance to the screen. Again, m equals 5. I'm just reading through. Theta is 1.422 degrees. L is 3.90. We know the slit separation, D, and by the way, this is in meters. We need to get this millimeters in SI units. That's 1.35 times 10 to the minus 4 meters. So we want the wavelength. Y over L, we don't necessarily need that per se, because we know that we have the angle. So we can just say D times sine theta bright divided by m is lambda. So just put the numbers in. Let's see what I get for lambda. 1.35 times 10 to the minus 4. And we can use the exact value times the sine of 1.422 degrees. Close out the parenthesis, close out the numerator, divide by m, and m is 5. Okay, so we've got 6.7 times 10 to the minus 7th. So that's 6.7 times 10 to the minus 7th, and that's going to be meters. But remember, I know we discussed this before, the most common scale that is used for visible light is nanometers. So this would be 670 nanometers, because nano is times 10 to the minus 9th. If light of wavelength 690 nanometers is used in a double slit experiment with slit separation 0.206 millimeters, what angle separates the two fourth order maxima? I'm going to suggest we solve for one of the angles and then we just double it. Because basically, if you think about the geometry, so there's a right triangle here with respect to the angle on one side. So again, this is some bright fringe, and this is, again, m equals 4. Again, m or n, doesn't really matter, integer. But then over here, there's going to be another right triangle. So we can solve for this angle, and then just do times 2. Just double it because of symmetry. Okay? So I think that's going to be the easiest way to deal. We know the lambda. That's 6.9 times 10 to the minus 7th meters. And we know that the slit separation, that's D, is again 2.06 times 10 to the minus 4th meters, because that's often in millimeters. So we want the angle. I think we can come back to this equation before, this time solve for the angle by saying m lambda over D, and then take the inverse sine, should give us the theta bright. And then again, remember, we have to double it at the end. Let's see, inverse sine of, and then again, these are fourth order, so m is 4, so it's 4 times lambda, 6.9, times 10 to the minus 7th power, and then divide that by D, which was 2.06 times 10 to the minus 4. Close off the parentheses. I'm hitting it with inverse sine. So I've got this angle is about 0.767 degrees. So if we double that, again, we've got to do times 2 to get our answer. If I just double that in my calculator, because of symmetry, I've got about 1.5353. So 1.54 sounds about right. Freaking laser beam!
I have one simple request, and that is to have sharks with frickin' laser beams attached to their heads.
Plus and minus 2, okay, are separated by 2.0 centimeters on the screen in a double slit experiment. What is the separation of the m plus or minus 3 maxima? Assume the angles are very small. So here's the deal. Again, let's use symmetry. So the idea is that if this is our right triangle to one of the maxima, the bright fringes, That is, at this point where m equals 2, and you get a fringe, that if both triangles give you 2 centimeters, that's here, then this distance right here has to be 1.0 centimeters, just by symmetry. Again, it's nice and symmetric if everything's glorious. We want to know what the separation between the plus and minus 3 maxima is. There's a couple things we can do. What we can do is we can kind of reuse certain things in the equation. So let's go back to the equation. Sine theta bright, and let's label this as the theta bright of m equals 2 equals m lambda. Now for one thing, d and lambda don't change if you move out here to the third maxima, right? This is m equals -3 down here. Above the page here would be the m equals +3 maxima, but you get the idea. So the idea is that they also said you can assume that the angles are very small. Well, it turns out that one approximation we can make is we can say that y of, again, the m equals 2 over L, okay? And the reason I bring that up is because L, the length to the screen, isn't going to change. Remember, we're approximating sine theta as approximately tan theta. Just like the ideal gas law, whenever things don't change and we collect them together as constants, and only 2 things change, namely the y position and the m, we can collect constants together. So I'm going to recommend d, L, and lambda are all constants. So we can say, watch this, d over lambda L, those are all constants on the left-hand side. If I divide by lambda and introduce L here, is going to equal to m over y. But notice that m over y, that's basically a constant. So you could say m in the first situation over y in this first situation is equal to m in the next situation over the y in the second situation. And we just have a ratio. We're just looking for y3. There's a couple ways to do this, but we could cross multiply. So we've got m2 y3 is m3 y2. So that's y3 is, let's see, m3 y2 over m2. And then the numbers put into that is just m3 is just 3. y2 is 1.0 centimeters. And then over here we've got 2. So 3 over 2 is just 1.5. So that gives us 1.5 centimeters because it's 3 over 2, 1.5 times this 1. And then remember, we got to double it again. Because again, if you're going to go from +3 to -3, the total distance between them is going to be 3.0 centimeters. So that would be our answer. So I'm thinking it's E. So choice E for 3.0 centimeters. All right, 11, using a double slit with D equals 300 nanometers and the wavelength of light is 400 nanometers, what would you see on a distant screen? In order for diffraction to occur, the width of the slit needs to be of similar size to the wavelength of the wave actually coming in. If the distance between the slits is only 300 nanometers, that's actually pretty small, because usually the distance between the slits is like a few millimeters, which is actually a lot bigger than nanometers. This is going to look very much like a single slit. If you have a slit that's wide enough to cause diffraction, those two slits are so close to one another, it's almost going to act like a single slit. Because you figure 300 nanometers is even less than the wavelength of the light itself. So what does a single slit look like in terms of its diffraction pattern? Well, if you remember, the intensity is greatest in the center and gets less as you go outward, and there's still fringes, but the fringes are sort of more narrow to some extent. So I think what you've got for A is correct, but let me just reread these choices quickly. So the intensity is maximum at the center and gradually decreases to either side. Okay, so that seems pretty good. Let's see, B, the intensity is maximum in a single narrow line in the center. Yeah, that's not going to be true because we're still going to have some diffraction. They didn't tell us what the width of the slits are, but let's assume these are like regular sort of width slits. The intensity is minimal in a single narrow line at the center. That's definitely not true. The central bright fringe is always the brightest in the center. And D, the intensity is minimal at the center and gradually increases. That's not true either. So yes, I think you came up with the right answer for A. A Young's double slit experiment is performed and then repeated after moving the screen to 3 times the previous distance from the slits. What happens to the angular separation as measured from the slits in the 4th order maximum? Correct, there is no change. Now the reason there's no change is because remember the equation from the previous board. D sine theta is equal to m lambda. We haven't changed m, lambda, or d, so the theta doesn't change. And another way to think about this is that if you take this right triangle and you move the screen back, all you've done is you've essentially kept the same angle, but just scaled this triangle up. I mean, that's literally all you did, because you just moved the screen back. The angle is the same, and yes, the y will be larger, but the L is larger, but they're proportionally larger to each other, so that the theta is the same. So this is the whole idea of similar triangles. So that's exactly correct. So hopefully you now understand why the double slit experiment is so important and how you can accomplish calculations with it. So what is diffraction? It's the spreading out of a wave from a source, and it turns out that each of those slits in the double slit experiment acts as a source of new waves. And when we spread that wave out, that depends upon the wavelength, but it also depends upon the distance between the sources. In this case of today's video, the distance between the slits also depends upon how far away you are and various things. So when it comes to real-world applications, the adage I want to leave you with is this: you can hear around corners, you cannot see around corners. Why is that? It's because sound has a much larger wavelength than visible light does. So when sound goes round a corner, the sound wave can much more easily bend, that is diffract, whereas the light wave itself is not going to do that. Even though light will experience some reflection, you certainly can't see around a corner. So notice that we use our ears for certain situations, and for certain applications we use our eyes for other applications. Even though our eyes take in more information than our ears do, our hearing is essential to how the body is designed and for when we are prepared for when something comes about. So hopefully you understand that from today's video. Thank you for watching High Peak Education. Please let us know in the comments how you're going to use this information in your physics classes or out there in the real world. And please smash that like button if you enjoy this content. And subscribe to the channel, and please ring that bell so that you never miss a video, that you help us grow the channel and you continue to receive benefit. We can keep making these videos to serve you. Also, please like our business pages on social media. Also, we have a Patreon page if you'd like to donate and participate. And thank you for watching. I will see you in the next video.